In the last video, we considered the amplitude shift keying. It changed the amplitude. It was some kind of digital amplitude modulation. And now we take the phase modulation to the digital domain and consider the digital phase modulation. And this is the phase shift keying, or in short, PSK. Here again, we get a symbol stream here. Oh, it's not the data, of course, that are symbols. And this is given to a digital phase modulator, and we get the radio frequency signal. And again, we do not consider the technical realization here. So this can be done in the digital domain or in the analog domain, or a hybrid solution in both digital and analog domain. But that is not important. We only care about the basic principle behind the phase shift keying. The last video ended with this representation here of the discrete states in the Phasor representation. Remember, our RF signal is a modulated carrier. So here our monochromatic carrier, the RF signal, and this is the phasor, so the complex amplitude. And the complex amplitude contains the actual amplitude and the phase. Remember this. And the ASK affected the amplitude, and now the PSK affects the phase. So here in this diagram, the possible phasor states are depicted. So here in this phase shift keying, there are 2 discrete states, and here there are 4 states. But now let's start with the case of 2 states. So whereas the states for the phase modulation, remember the last video, were aligned on the positive side of the real axis, we have now this situation. And the discrete states are located on the unit circle here and here too. There's also the unit circle. So the amplitude is equal for both states. Amplitude is equal, as well as here, equal amplitude. But what's different is the phase. So here, for in the upper example, for the phase for the symbol 0, we have a phase of 0, and for symbol 1, we have a phase of 280 degrees. Here in the example below, for this state, 0 degrees, 90 degrees, 180 degrees, and 270 degrees. So what changes is indeed the phase. The amplitude is constant. So now we have a series of symbols again. Here 2 states, 2 symbol states, and we can encode 1 bit of data and 1 symbol. Now we start with 1 here with the symbol 1, and the carrier oscillates, and then here at this point the symbol changes. goes to 0. And then here is a phase shift. So here the carrier signal is some kind of interrupted, and the phase jumps from 180 degrees to 0 degree. And then the symbol changes back to 1, and then to 0, and 1 again. And yeah. So the phasor in this representation jumps between these two states. And now we can add more states. So in the lower example, there are 4 discrete states, and we can again encode 2 bits of data in one symbol. Again, the symbol period is the inverse of the symbol frequency. Symbol frequency defines the bandwidth of the signal. So we can transmit more data within the same bandwidth. Yeah, and to maybe explain again why the bandwidth is important, let's consider that you have different users, and the users share an RF band. For example, there's a user here at this frequency, and another user is here at this frequency, 868.2. And now if you want to transmit more data but don't want to add more discrete states, then the transmission bandwidth would be enlarged. And here you see that this enlargement would disturb the other user. So the other user must be shifted away, but the frequency bands are a sparse resource. So for example, this would not be possible because this frequency is maybe allocated to another service. Yeah, so it's feasible to encode as much symbols, as much data in one symbol as possible. So in the example below, 2 bits are encoded in one symbol. And again, this comes at a drawback that this constellation is less immune to noise. But however, let's look how this example works. So we start with 0, and then we go to symbol 3. So we have a phase shift, a phase jump by minus 90 degree, and then it jumps to 1. So there's a phase shift of 180 degree, and then to 2. And these phase jumps can be seen here. Yeah, so the symbols are just encoded in the phase of the carrier.